Flip a coin and slap it down on the back of your hand. Right now, under your palm, it's decided, heads or tails, one or the other, even though you haven't peeked. Fine, now do something different. Spin it. Set it whirling on the tabletop, that silver blur, and freeze the film right there, mid-spin, before it topples. And ask yourself the strange little question, what is it showing in that instant? Not heads, not tails, something your two small words can't quite hold. Hang on to that blur, because tonight I want to tell you about a coin the universe genuinely builds, and while it spins, it is doing a thing that no coin on your kitchen table ever could.
That's the right place to start, and I love that you started with the blur, because the blur is the whole of it. The blur is where the story lives. Most people, when they hear the word qubit, picture some tiny gadget, a smaller switch, a faster bit. And it isn't that at all. It's the blur. It's what you just froze on the tabletop. And the job of tonight is to take that blur seriously. More seriously, I promise you, than you're going to be comfortable with.
Good. Ruin me the way you ruined me last time, but do me a favor and start on solid ground, because last time we spent a whole evening on one idea, and I want to make sure I'm still standing on it. We said, information is physical.
We did. And that's exactly the ledge to stand on. Say back to me what it meant. Standing on solid ground, the bit.
It meant that information isn't some airy, abstract thing floating above the world. A bit isn't a ghost. Every bit you've ever stored had to ride on something real. A patch of magnetism on a disk, a little bucket of electric charge, a pit stamped into a plastic disk. The 0 and the 1 always have to be written down in some piece of the physical world.
Beautiful. So hold that thought, and let's look hard at the ordinary bit, the one your whole world runs on, before we dare to touch the strange one. What is a bit, physically? Picture the simplest thing you can, a light switch on the wall.
Up or down, on or off.
Up or down. And notice the two things that are true of that switch, because they're so obvious you've never once said them out loud. First, there are exactly two positions it's allowed to rest in. Not three, not a half. Up or down. Second, and this is the one that matters tonight, at any moment it is definitely in one of them. Even in a pitch-dark room, even with nobody looking, that switch is either up or it is down. It has a fact about itself, sitting there, whether or not anyone reads it.
Right, and if I walk in and flip the light on, I'm not creating the answer, I'm just finding out which way it already was.
You're just finding out. Write that sentence on the wall, because in about 20 minutes, I'm going to walk over and cross it out. For the ordinary bit, it's dead true. Looking only reveals what was already so. The bit has a secret, and reading it spills the secret, and the secret was sitting there the whole time. That is the entire, comfortable, sane world of classical information. Two definite positions. Reading tells you which. Nothing you didn't already, in principle, know.
And that's the world my laptop lives in. Billions of these little switches, each one honestly up or honestly down, and the machine just reads them and shoves them around.
Billions of honest little switches. Every photo, every song, every word anyone has ever typed, all of it, in the end, a vast field of switches, each one committed to up or down. That's the atom of the ordinary world. Now, let's build the other kind, correcting our own hook.
The spinning coin.
The spinning coin. And here's where I have to do the thing I promised you last time I'd always do, even when it costs me. I have to spoil my own opening, because the spinning coin is a lovely picture, and it is not quite right. And if we don't fix it now, it'll quietly lie to you for the rest of the course.
Go on then. What's wrong with my blur?
Tell me this. That coin spinning on the table, is it really undecided? Or is it just that you can't tell yet?
It's just that I can't tell yet. If you knew everything, the exact spin, the wobble, the little imperfections in the table, you could in principle calculate exactly how it's going to land. It's already secretly on its way to being heads. I just don't have the information.
There it is. The spinning coin is not genuinely poised between the two. It is a perfectly ordinary object, its fate already sealed by the push you gave it, and the blur is nothing more than your ignorance smeared across time. It's a hidden answer, not a missing one. Under the blur, the coin is still playing by the switch rules, still definitely going to be one thing. You just haven't been let in on it.
So my beautiful hook is a fake.
Your beautiful hook is a classical coin, and classical coins can't do the trick. But it's the perfect fake, because now you know exactly what we need the real thing to be. We need a coin whose in-between is not you being ignorant. We need an in-between that is genuinely, physically there. An in-between the universe itself hasn't resolved and isn't secretly hiding. That's the qubit. And the universe, it turns out, builds those. It builds them out of its smallest pieces. What a qubit actually is.
Out of what, though? You keep saying the universe builds one. If a bit is a patch of magnetism, what's a qubit made of?
Something just as real. This is the information is physical thread again, still in your hand. Take a single electron. An electron has a property we call spin, and for our purposes, it behaves like a tiny compass needle that, when you ask it a plain up or down question, only ever answers up or down. Or take a single particle of light, a photon. It has a polarization, a little orientation, horizontal or vertical. Or a single atom, which can sit in its calm, lowest energy state, or a lifted, excited one. Any of these, spin, polarization, atom, is a real physical thing in the world with two special settings. Call them the 0 and the 1.
So there's my two switch positions again. Where's the coin blur?
The blur is what these tiny things get to do that the switch does not. An electron's spin does not have to be honestly up or honestly down. It is allowed to sit in a genuine in-between, the real kind, not the ignorant kind. Physicists have a word for that in-between, and it's the word this whole episode is really about. Superposition.
Superposition. All right, that's the word I hear thrown around everywhere, always with jazz hands. It's 0 and 1 at the same time. And honestly, it always sounded like a magic trick I wasn't allowed to inspect. So inspect it for me. Slowly.
I will. And I'm going to inspect it so slowly that we take that jazz hands phrase apart screw by screw, because it's doing real damage out there. Let me give you the honest picture first, and then let's murder the myths one at a time. Superposition, told honestly. Here is the honest picture. A qubit state is a blend. It is made of some amount of 0 and some amount of 1, mixed together in specific proportions. And crucially, it is one single definite thing. The blend itself is the state. It's not two states secretly coexisting. It is one state, and that one state happens to be a mixture.
Give me something to hold that with. A blend of two ingredients. Like what?
Like color. You know exactly what I mean if I say a particular shade of purple. Purple is a genuine, single color. You can point at it. It's right there on the wall. It's one definite thing. And yet it's a blend. Some red, some blue, in a particular ratio. Now, is purple red and blue at the same time? In a loose, drunk at a party sort of way, sure. But if you say it carefully, that phrase is nonsense. The wall isn't flickering between red and blue. It isn't secretly red and also secretly blue, and you catch it in the act. It's purple. One color. A definite point that happens to sit between two others.
So when someone says the qubit is 0 and 1 at the same time.
They're saying the wall is red and blue at the same time. It's the party version. And here's the harm in it. That phrase smuggles in a picture where the qubit is secretly both answers, two little hidden values riding along together, so that surely, if you were clever enough, you could pull both of them out. And you cannot. That picture is exactly the thing that's going to break your heart later tonight. The qubit is not 0 and 1, it's a third thing, a purple, a blend that is its own honest single state.
Okay, let me try to say it in my own mouth. It's not that it's hiding two answers. It's that it's genuinely in a state that is neither answer. A new state, in between, that only classical thinking forces me to describe using the two words 0 and 1.
That's it. That's the whole reframe, and you found it faster than I did. The two words are ours. They're the only two answers our crude question can get back. The qubit's in-between is a place our language doesn't have a native word for, so we're stuck describing it as a bit of this, a bit of that. But the thing itself is one definite state. Now, if it's one definite state, sitting somewhere between the two, then I ought to be able to draw you a picture of where. And that picture is the most useful thing I can hand you tonight. From two poles to a whole globe. Go back to the light switch. How many places can it be? Draw them for me in your head.
2. A dot for up, a dot for down, 2 lonely dots.
2 lonely dots. Now I want you to take those 2 dots and pull them apart until they're the North Pole and the South Pole of a globe. A ball, like a little Earth. 0 sits at the North Pole. 1 sits at the South Pole. So far, I've told you nothing new. I've just drawn your 2 switch positions at the top and bottom of a ball.
Fine, 2 poles. Where's this going?
Here's where. A classical bit is only ever allowed to be at one of the 2 poles. Nowhere else on the ball is legal. But a qubit is allowed to point anywhere on the entire surface of that globe. Every city, every ocean, the whole skin of the sphere. Picture a little arrow from the center of the ball out to a point on the surface. That arrow is the qubit state. Point it dead north, that's a clean 0. Point it dead south, that's a clean 1. But point it at the equator, out over the ocean somewhere, and that's your blur. That's superposition. A real definite direction that simply isn't either pole.
Oh, that's gorgeous. So the switch lived at 2 dots and the qubit lives on the whole globe.
The whole globe. And I want you to feel how much bigger that is. Between the 2 poles, there is one single place a bit can be. Well, 2, the poles. But a qubit has a continent's worth, an ocean's worth, an entire planet's surface of legal places to point. Infinitely many. That is the first jolt of the thing. You went from 2 options to a smooth, unbroken world of them.
All right, and this ball has a name, I'm guessing, because you physicists can't help yourselves.
It's called the Bloch sphere, after a fellow named Bloch, and the name doesn't matter a jot. The globe matters. Keep the globe. Now let me hand you the 2 dials that steer the arrow around it, because there are exactly 2, and they are the 2 most important numbers in the qubit's life. The 2 dials, the odds and the twist. First dial. How far the arrow tips down from the North Pole. Its latitude, if you like. Are we up near the North Pole? Down at the equator? Slipping toward the south? That 1 dial, the latitude, sets the odds. And hang on to odds, because in a few minutes it's going to be the hinge of everything.
Odds of what?
Patience. That's the next section, and it's the good one. For now, just hold the meaning of the latitude. An arrow up near the North Pole is mostly 0, leaning that way, only a little 1 mixed in. An arrow slid down near the South Pole is mostly 1. And an arrow sitting right on the equator is the perfect, balanced blend. As much 0 as 1, dead even, the 50-50 coin. Latitude is the mixing ratio. That's dial 1.
Latitude is the recipe. How much 0, how much 1, got it. And dial 2?
Dial 2 is which way around the arrow is turned. It's longitude. Imagine the arrow sitting on the equator, and now, keeping it on the equator, you swing it around, pointing due east, then south, then west, then north around the ball, all the way round the circle. Same latitude the whole time, same recipe, same 50-50, but it's turned to face a different direction around the axis. That longitude has a name too. We call it the phase.
Phase. And what does the phase change? If I keep the arrow on the equator and just spin it around to face west instead of east, the recipe's the same, you said. So what did I actually change?
Now you've put your finger on the strangest, most quietly explosive thing in the whole subject, and I'm going to answer you honestly and then ask you to not be satisfied. Here's the honest answer. For the one simple measurement we're about to do, the plain up or down question, swinging the arrow around to a different longitude changes nothing you can see. The odds are set by the latitude, and you didn't touch the latitude. East-facing and west-facing give you the identical coin flip.
So the phase is decoration? A number that doesn't do anything?
That is exactly what it looks like tonight. Idle decoration. A dial you can spin with no effect. And I'm telling you now, so you can watch me be right later, that innocent, useless-looking dial is the single most important thing in this entire course. It is the secret ingredient. It looks dead tonight because we've only got one lonely qubit and one crude question. But the moment, a few nights from now, that we learn to make two of these arrows meet and combine, their phases, their longitudes, are what decide whether they add up and reinforce or cancel and wipe each other clean out, like two waves crossing on a pond. The whole magic of the machine is going to live in that dial. So put a pin in phase, a big one. We are not done with it, we've barely met it.
A dial that does nothing. That's secretly everything. Filed. Pinned. I don't like how many pins you're giving me already.
The coat's going to be full of them by the end, same as last season. But now, the moment I've been stalling, we have this arrow pointing somewhere on the globe. A whole planet of possibility. Let's do the one thing you're actually allowed to do to it. Let's look. Measurement. The universe only answers yes or no.
Looking. I look at the qubit, the arrows pointing at, say, some spot up in the northern hemisphere, mostly 0-ish. What do I get back?
What do you want to get back? Be greedy. In your dreams, what does the qubit tell you when you look?
In my dreams? It tells me the arrow. It says I'm pointing there, this latitude, that longitude, this exact spot on the globe. It hands me the whole direction.
Of course it does, in your dreams. And now the universe wakes you up. Because here is the iron law of measuring a qubit, and it is brutal in its simplicity. When you look, when you measure, the universe will not give you the arrow. The universe will only ever answer you with one bit. 0 or 1. A single yes or no. That's all it can say. That's all it will ever say.
Wait. I built this whole rich thing, a direction out of an infinity of directions, a precise spot on a globe. And when I ask it what it is, all I get back is one lousy 0 or 1.
One lousy 0 or 1. The globe has a continent's worth of places to point, and the answer slot has room for exactly 2 words. So which word do you get? That's what the latitude was for. The arrow's latitude, how it was leaning, sets the odds of the answer. Arrow up near the North Pole, you'll very probably hear 0 and just occasionally 1. Arrow down near the South Pole, probably 1. Arrow smack on the equator, the balanced blend. It's a true coin flip, 50-50, no way to call it.
So the measurement is genuinely random.
For a real superposition. Genuinely irreducibly random. Not spinning coin random, where the answer was secretly settled and you were just ignorant. This random. The arrow was leaning at the equator. The universe had not decided, and in the act of looking it decides, right then, for the first time, and it decides by weighted chance. There is no earlier fact you failed to read. There was no hidden answer. The answer is born in the looking.
That's the sentence you told me you'd come cross out. Looking only reveals what was already there.
Go and cross it out. For the honest bit, looking revealed a secret that was already sitting there. For the qubit, looking creates the answer that wasn't there a moment before. That is the deepest difference between the two worlds, and it's the one people skate right over. Reading a bit is discovery. Reading a qubit is more like a birth. Collapse. The arrow snaps to the pole.
Okay, but here's what's nagging me. Say I measure and a universe coughs up 0. Fine, what happens to the arrow, the actual physical thing after that? It was pointing out over some ocean. Where's it pointing now?
Now that is the exactly right question, and the answer is the part that gives the whole thing its horror movie name. The instant you measure and hear 0, the arrow doesn't stay out over the ocean. It snaps. It jumps, in that instant, to point dead north, to the pure 0 pole. All that rich in-between direction it had, all that latitude and longitude you so carefully built, gone, flattened. The arrow is now simply, boringly, at the North Pole, as committed a 0 as any dull classical switch.
It collapses.
It collapses. That's the word, the collapse of the state. The globe's worth of possibility crashes down onto a single pole the moment you look, and it keeps whichever pole matched your answer. And to prove the arrow's really stuck there now, measure it again, straight away. What do you think you get?
If it snapped to the North Pole, then, measuring again, the odds are now 100% 0. I get 0 again. And again. It just keeps saying 0.
Every single time, forever. 0. Dead certain. Because it's not a blend anymore. You looked once, and your looking drove it to a pole and left it there. The very first measurement doesn't just read the qubit, it changes it. It reaches in and slams that gorgeous arrow flat against a pole, and after that there's nothing rich left to find. You get one bit out, once, and the price of that one bit is the entire rest of the globe.
That's almost cruel. You spend all this effort pointing the arrow at some exquisite spot, and the very act of checking where it points destroys where it points.
Cruel is the right word to sit with for a second. But before you decide it's only cruel, I owe you the piece that turns it from a party trick into something that ought to raise the hair on your arms. Because you might be thinking, fine, it's random, the answer's born when I look. But maybe the arrow was never really somewhere definite at all. Maybe a definite direction is just a story, and really there's only the coin flip. Let me show you that the direction is real, bone real, and I can do it with one clean demonstration. The demonstration that the direction is real. I'm going to build you a specific qubit. I'll set its arrow on the equator, perfectly balanced, 50-50, 0 or 1, and I'll turn it to point due east. A specific longitude, a definite, particular arrow. You with me? Equator, pointing east.
Equator, east. A dead-even blend, turned a particular way round. Got it.
Now you walk up and ask it the ordinary question. The up or down, north-south, 0 or 1 question. What happens?
It's on the equator, so it's 50-50. Coin flip. I get 0 or 1 at random, and the arrow snaps to whichever pole, same as before.
Exactly. By that question, this qubit looks like pure noise. A coin. Useless. Now here's the move. I build the same qubit again. Equator, pointing east, but this time you don't ask it up or down. You turn your whole measuring apparatus sideways and you ask it a different yes or no question. Not north or south, but east or west. You ask it along the very axis it's already pointing down.
East or west, along the equator instead of up the poles, and the arrow's pointing dead east already, so
So what do you get?
I get east. Definitely, for certain, every single time, because the arrow is pointing east. I lined my question up with the way it was actually leaning, so there's no in-between anymore. It's a pole as far as that question is concerned.
Every time. Dead certain. And now feel what just happened, because this is the whole ballgame. The same physical qubit gave you pure, hopeless randomness when you asked it north or south, and gave you a perfect, certain, repeatable answer when you asked it east or west. If that arrow had been nothing, if it had really been an empty coin with no direction, it could never have answered anything with certainty. But it did. It had a genuine, definite property sitting there all along. It was really pointing east, and the up or down question simply wasn't the question that property answers.
So measurement isn't the universe reaching into a bag of no answers and inventing one. The arrow was really there. It's that the arrow points one way, and my measuring apparatus points some other way, and the answer I get is about how those two line up.
That is the honest heart of measurement, and you just said it clean. Every measurement is a question with a direction. You choose an axis, and you ask the arrow, which side of this axis are you on? If your axis happens to line up with the arrow answers with perfect certainty and doesn't even flinch. If your axis is crosswise to the arrow, you get the weighted coin flip. And either way, the arrow snaps to lie along the axis you chose. The randomness was never the arrow being empty. The randomness is the mismatch between the question you asked and the way the thing was actually leaning.
Okay, that genuinely reorganizes my head. The qubit always has a definite direction. I just almost never get to ask the one question that direction wants to answer, and asking any other question wrecks it.
And now, you're standing right on the edge of the thing this whole course is built around. The tension that's going to haunt every single episode after tonight. Do you feel it already? Say what you're feeling. The tension that haunts the whole course.
I think I do. Let me try. I can build this qubit pointing anywhere, any spot on the whole globe, a precise latitude, a precise longitude, out of an unbroken infinity of directions. To specify exactly where I aimed it, I'd need a stack of numbers. Really endless precision, endless digits of latitude and longitude. So in some sense, I've loaded an enormous amount of information into this one tiny thing.
An infinity of it, in principle. Go on. You're doing the hard part.
But when I try to get it back out, the universe hands me one bit. 1, 0 or 1. And the looking itself smashes the arrow flat, so I can't even go back and ask again to squeeze out more. I put a whole globe in, and I'm allowed to take exactly one bit out, once, and the taking destroys the rest.
There it is. You can't read out everything you put in. That's the sentence. Say it again, slowly, because it is the single most important idea in this entire course, and everything clever anyone has ever done with a quantum computer is a way of wrestling with it.
You can't read out everything you put in.
You cannot. You can pour a globe of information into a qubit, and the universe will only ever let you draw one bit back out, and it charges you the whole globe for that one bit. It is, on the face of it, the worst storage device ever conceived. Imagine a library where you may write as many books as you like onto a single page, but you're allowed to read exactly one word, once, and the instant you read it, the whole library burns to the ground.
That's a terrible library. But hang on, let me try to cheat my way out. Before I look, why don't I just copy the qubit? Make myself a stack of identical arrows, all pointing the same way it does. Then I measure the first one up and down, the next one east and west, the next one some other way, and I triangulate. I ask all the questions on all the copies, and I reconstruct the whole arrow. There, I've beaten your one-bit rule.
That is the smartest possible thing to try, and I want you to feel the ground for how smart it is. Because it's exactly what you do with a classical bit. Copy it 1,000 times, poke each copy, learn everything. And the universe has closed that door too. It is one of the deepest facts in the whole subject. You cannot copy an unknown qubit. There is no machine, and there never will be, that takes a mystery arrow and spits out two of it. Nature simply forbids the photocopier.
It forbids? Wait, you can't copy it? Why on earth not? That feels like it should be the easiest thing in the world.
It feels that way because copying is free in your world. You've copied files your whole life. And the why of the ban is a genuinely beautiful argument that I am not going to spoil tonight because it's got a whole episode with its name on it later on, and it's the very thing that will let us protect these fragile arrows from noise. For now, just carry the fact and feel how it slams your last escape hatch. You can't read the whole arrow, and you can't copy it to read it in pieces. One arrow, one question, no do-overs.
So the cheat's dead too. Then genuinely, if I can't get the information back out, and I can't even photocopy it, what on earth is a qubit good for?
And that exact objection is the door into the rest of the series, so I want to answer it carefully and then leave the rest hanging, because it's not tonight's to finish. The bug that is secretly the feature. You're looking at it as a storage box, and as a storage box, it's a disaster. But it was never a storage box. Here's the reframe, and it's the one that flips the whole thing from a curse into the most exciting idea in modern physics. The trick of quantum computing is not to stuff a globe in and hope to read it all back. We just proved you can't. The trick is to be clever about the one question you're allowed to ask. To spend your whole computation quietly steering that arrow, nudging its latitude, twisting its phase, that useless dial, so that when you finally do look, the one bit that falls out is the answer you actually wanted.
So you don't fight the one-bit rule, you aim at it. You spend the whole calculation arranging for the single bit you're allowed to read to be the one bit worth reading.
You aim at it. The measurement isn't the enemy. It's the finish line, and the entire art is arranging the race so you cross it in the right place. And remember that pinned dial, the phase, the longitude I told you looks like idle decoration. That's the steering wheel. Because when we learn to bring qubits together, their phases will let the wrong answers cancel each other out, wipe themselves off the board like two waves meeting crest to trough, and leave the right answer standing tall so that the one bit you're allowed almost can't help but be correct. That is the real machine, not try every answer at once. That's the party version, and it's wrong, and we'll spend a whole night killing it properly. The truth is stranger and better. Make the wrong answers erase themselves.
And you're going to make me wait for that.
I'm going to make you wait for that, because you can't feel it yet. You're one qubit tonight, and that trick needs at least 2 arrows meeting. Which is where next time comes in. Because I've told you a single qubit is a whole globe of possibility. What I have not told you is what happens when you take 2 qubits and let them fall in love.
Fall in love. That's a suspicious way to put it.
It's the only honest way I've got. 2 qubits can be joined so tightly that neither one has a direction of its own anymore. The arrow belongs to the pair, not to either qubit, so that touching one instantly says something about the other, even if you've carried it to the far side of the world. It unsettled Einstein for the rest of his life. It's the strangest thing in this entire subject, and it is the fuel that every miracle in the back half of this course is going to burn. But it is emphatically not tonight's. Tonight was one arrow, one globe, one question. Landing the vertigo.
Then let me try to gather up the one arrow before you take it away, because I want to make sure I can carry it out the door. A classical bit is a switch, 2 positions, and it's honestly sitting in one of them whether or not I look, and looking just tells me which. That's the whole sane, comfortable world my laptop lives in.
The whole comfortable world. And the qubit?
The qubit is not a switch, it's an arrow on a globe, free to point at any spot on the whole surface, an unbroken infinity of directions, a real, definite in-between that isn't hiding 2 answers, it's genuinely a third kind of thing, like a purple that isn't secretly red and blue, and 2 dials steer it, the latitude, which sets the odds, and the phase, the longitude, which does nothing I can see tonight, and turns out to be the secret of everything.
Keep going. Bring it home.
And when I look, I don't get the arrow. I never get the arrow. I get one bit, 0 or 1, weighted by how the arrow was leaning. And the answer is born in the looking, not dug up from some hidden fact. And the looking slams the arrow flat against a pole and burns the rest of the globe away. So I hold a whole world of possibility in one tiny thing, and I'm allowed to ask it exactly one yes or no question. And the asking of it destroys the world I was asking about.
You are holding a globe. You are allowed one question, and the question, when you finally ask it, burns the globe down to a single point. Sit in that for a second, because that's not a limitation we're going to engineer our way around. That's the deal. That's the actual physical deal the universe offers for touching information at its very smallest. And the whole rest of this series, every algorithm, every unbreakable code, every golden machine colder than deep space, is human beings being clever, being heartbreakingly clever about that one deal, about the one question we're allowed to ask.
A globe you can't read, and one match to strike, and everything rides on where you're standing when you strike it.
Everything rides on where you're standing when you strike it. That's the qubit. That's the whole of it. And next time, we strike 2.
I came in tonight thinking a qubit was just a faster switch, and I'm leaving with a planet I'm not allowed to look at. I'll be turning that one over for a long while. Good night.
Good night. Mind the arrow on your way out. And don't you dare measure it.